The aurora borealis is a spectacular display seen in the sky of the far north. It is caused by the sunlight moving the electrons in the atoms of the gases of the atmosphere. Similar color effect can be created in a simpler way in the lab by heating the compounds of some metals in a Bunsen flame burner. Those colors are also created by moving the electrons in the atoms of the compound that we heated. But how do the electrons move inside the atom to create such colors? And does their place inside the atom have something to do with their emission of these colors? In 1913, Niels Bohr, working with Ernest Rutherford, developed a theory to explain how electrons were arranged in atoms. This theory helps to explain how the colors in the flame test are produced. And we can summarize a simplified version of Bohr's atomic theory of the arrangement of electrons in an atom, and it goes like this. Electrons are in orbit around the central nucleus of the atom. The electron orbits are called electron shells or energy levels, and they have different energy. The shells that are further from the nucleus have higher energies. The shells are filled with electrons, starting with the one with the lowest energy, which means the closest shell to the nucleus. The first shell in any atom can only hold 2 electrons and nothing more. The second and other higher shells can hold up to 8 electrons to give a stable arrangement of electrons. This atomic theory made it possible to draw a full subatomic representation of any atom, just by knowing the number of electrons that the atom has. Let's take carbon as an example. Carbon has 6 electrons. So if we want to distribute the 6 electrons on the shells of the carbon atom, the first shell will have 2 electrons, and that would left us with 4 electrons. So we place them in the second shell. Keep in mind that for an atom to be stable, it must have either one shell only filled with 2 electrons or to have the last shell filled with 8 electrons. So if we apply that to the carbon atom, we will see that the last shell is not filled with 8 atoms, so the carbon atom is not stable as a single atom. The electron arrangement, or what we may call the electron configuration, can also be presented in a simpler way using numbers only. For instance, we can write the electronic configuration for carbon like this, with 2 electrons in the first shell and 4 electrons in the second shell. And that way represents to us that we have 2 electrons in the first shell and 4 electrons in the second shell, and a total of 6 electrons for the whole carbon atom. You should also remember how to work out the electronic configuration for the first 20 elements in the periodic table and how to draw them in rings. Electron arrangement is the key to understand and predict the properties and characteristics of an element. The properties and the characteristics of each element when compared to the other elements are the basis of how all known elements are arranged in the periodic table. You can directly link the electronic configuration of an element to its position in the periodic table. The number of electrons in the final shell of an atom is the same as the group number of that element, and the group number is the number of the vertical columns that an element is in the periodic table. Now, the number of shells that the atom has represents the period number, and the period number is the horizontal row on the periodic table that an element is in. For instance, the electronic configuration for sodium is 2, 8, 1. As you can see, sodium has only 1 electron in its final shell. This means it is in the first group in the periodic table. And it has 3 shells. This means it is in the third row in the periodic table. And if we go and check the position of sodium in the periodic table, we will find it in the first group in the third row. The term noble gases is used to describe the elements in the 8th and last group in the periodic table. The noble gases are very unreactive gases. The atoms of the noble gases elements all have a very stable electronic configuration. This means their atoms exist naturally as a single atom. Noble gases also do not make chemical bonds with the atoms of other elements, either by sharing or transferring their outer electrons. They all have a full outer shell of electrons. This means that they usually have 8 electrons in their last shell. Just know that when atoms of elements other than the noble gases combine to make molecules, they often try to achieve the same stable arrangement of electrons as the noble gases. And we will discuss that more deeply and thoroughly in further videos. This was everything for today's video. Hope you find it helpful and see you again in the next video.